Hello everyone. We are the Quail Egg Embryo Extractor team from Portland State University's Massey College of Engineering and Computer Science. We will be presenting our capstone project sponsored by the Child's Cancer Therapy Development Institute. Our capstone is a hybrid between mechanical and biomedical engineering fields. We will be developing a quail egg embryo extracting device that will safely remove the content of the egg to conduct metastasis research. Our faculty advisor is Dr. Natalie Neve, a PhD mechanical engineering professor, and our industry sponsor is Dr. Charles Keller and his biomedical research team. Seen from left to right is Alex Arnold, Ann Ng, Sam Sanford holding the first prototype, Samuel Rasmussen, Josh Lake, and Baldur Steingrimsson, the founder of the ecosystem. Not shown is Robert Lesanovsky. At the Child's Cancer Therapy Development Institute, their mission is to make childhood cancer universally survivable, regardless of diagnosis, with an emphasis to focus on less toxic and more effective treatments. The primary goal for the project is to develop a device that safely and efficiently removes the embryo of a quail egg for cancer research. Our goal for the efficiency is to extract more than one egg per minute with a higher success rate of 50%. Our aim is 90%. Some of the secondary specifications of the device are the ability to accommodate the various egg sizes, sanitization, ease of maintenance, and ease of operation. More of the specifications will be shown in the ecosystem software later. Here, the current extraction process is illustrated. In step 1, the fertilized eggs are incubated for 72 hours and cleaned and moved to a warm slider to allow the yolks to float on top of the egg. In step 2, prior to the extraction process, the equipment and forceps are sanitized. The eggs are held above an empty well while keeping it upright at a tilted angle. The forceps puncture the shell and cut around the smaller end of the egg until the shell fragment is removed. The whole content of the egg then falls into the well with everything intact. To determine the survival of the embryo, the heart must be visible from the top and not underneath the yolk. In step 3, the embryos are injected with cancer and are ready to have various drugs tested on them. In step 4, the results are then observed. The second step in the testing process is the bottleneck of the project. Our role in the cancer research is to implement an efficient and safe process to extract all the content of the quail egg without any cross-contamination and damaging of the embryo. With this developing device and strategy, it will improve the efficiency and success rate of surviving embryos for the current implementation process. Here we see the first handheld prototype showing the manufactured handles, piston, tension springs, suction cups, and tubing. This is a quick video of the testing of the first prototype.
Alright, so we're going to demonstrate how the ecosystem has helped in the designing process of this project. So with the project goals, we have defined our project mission statement for this project. And for the problem definition, we have further identified the problem of this project. And we can also identify the customer for this project and also list the motivations for each of the customers. And for the requirement definitions, we have listed the customer requirements for this project and associate them to the specific customers. For the requirement analysis, we have defined the engineering requirements for this project, and we also have this objective function that can later help evaluate our designs. And each of the engineering requirements are rated for the level of importance from low to very high. Another function of this ecosystem that we like is that you can generate a scorecard that can compare the learning objective to the 8-bit learning objective. Also, you can also generate a preview and to print the scorecard of the 8-bit learning objectives. Alright, moving on to the conceptual design. We have listed 3 of the methods that we choose for our designs, and this can help evaluate which methods will be best fit for the project. So based on the rating, out of the 3 designs, the suction tension was rated the highest because it's the most reliable and offers more control. within the suction tension method, we have the kinematics as well as the suction of the design. And within the suction, we have three other designs that has been evaluated, such as the piston, internal vacuum pump, and the external vacuum pump. And based on that, the scoring card, the external vacuum pump was the most ideal for this project. And as you guys can see from the scorecard, the external excuse me, the external vacuum pump has 77, which is the highest. And in addition, we also has inputted a rationale of why we think that this design is the best fit for this project. In addition, we also compiled a overall summary to summarize the designs of this project and to assess which design is the best fit. And we can also define our confidence level for our evaluation of the final design, and to give a reason for why we chose this design. And I believe the ecosystems has helped us with the design and evaluating our design very thoroughly and confidently. Thank you for listening.